Hello, everyone, and welcome to my lab. This is the 28th annual Christmas lecture. It's done in the tradition of Michael Faraday. I promise you a very good time if you pay attention, especially to all kinds of different things that might be happening, including having a flame show up. And I want you to be on the lookout for color changes, for smoke. And I want you to be very, very, very attentive, but I would like you to sit back and relax and try as much as possible to keep track of what I do. So here's the first experiment we're going to do. Are you ready for this? Of course, when we do experiments in my lab, we obey the safety rules. That's why you see me wearing my goggles to protect my eyes, just in case something splashes into them. And we have a fire extinguisher right here, ready to be used, just in case something goes out of control. We're not planning on anything going out of control, but just in case as a safety precaution. I'll just set it aside here to be out of the way, but ready to be used. Now that balloon that I ignited with this big flame, what color was that balloon? Red. That balloon had a gas in it that combines with oxygen in the air in a very explosive way. That gas is called hydrogen. What we're going to do now is, as we always do in science, is repeat the experiments. We're going to repeat the experiment with this other balloon that's right here. But we're going to repeat the experiment in the dark. Okay, so with the lights out. Okay, here we go. Ready? All the lights down. And... Now, were you able to see things differently with the lights out than with the lights on? We want to keep that in mind. Every time we do an experiment that has to do with the release of energy in the form of light, we should try to keep the lights down. Actually, I'd like everyone now to look at the monitors because we're going to look at that very last reaction in slow motion. So watch and see. You won't hear any sound. There's the torch coming to the balloon and boom. There's that big, what color was that flame that you saw? Red, orange, red, yes. Well, we have other balloons. Do you see other balloons that we have here? Yeah. How many other balloons do you see? 4. All right, what we're going to do is find out what's in these balloons. What do you suppose we have in those balloons? That the red balloons had in them hydrogen. Some of you are saying helium. You know from experience that helium-filled balloons are lighter than air, so that's a very good guess. I will tell you that helium is a gas which does not burn like hydrogen did with the ignition with the torch. So we'll try this balloon now. Now I notice some of you are covering your ears. Why are you covering your ears? Because you learned that there might be some sound energy released, right? And so here, we'll try this balloon. And what happened? That balloon, did that balloon have hydrogen in it? That balloon had helium in it. Helium is a gas lighter than air that does not burn. It does not undergo this explosive reaction that we just saw and witnessed with the red balloons. Now, because sound energy is released and because it might be possible to damage our eardrums, I would like everyone to obey the safety rules before I do the next experiment by taking both fingers and putting them in your ears like this, okay? I can't do that and do the experiment at the same time, so I will use some earplugs that I have with me. And I really would like you to protect your eardrums. So if you can hear the sound of my voice, that means you don't have your ears well protected. Now, I can't hear you back, but I see some of you smiling. That means you heard what I just said. So I'd like you to protect your ears as much as possible as we go over to the next balloon that we have over here. Ready? Now that balloon had in it a mixture of hydrogen and oxygen. There was more oxygen available for the hydrogen to mix with when the ignition process took place. As we always do in science, we're going to repeat the experiment and we'll do it one more time in the dark. So please protect your ears one more time. And we'll turn the lights down. All the way down. You ready for this? Again, were you able to see things differently with the lights off than with the lights on? That's a very important thing to keep in mind. Let's take a closer look at this in slow motion. Once again, you won't hear any sound, but you will see the torch coming closer to the balloon and ignition. There. And you see it was a much faster reaction than the one with the balloon that had only the hydrogen in it. Now, as we do experiments in my laboratory, you never really know who is going to show up. We get lots of special guests. All of you are special today, but you never really know who might drop in as we go with our experiment.
Merry Christmas! Merry Christmas! Merry Christmas! Merry Christmas! Merry Christmas, Miss Sam!
Merry Christmas to you too, Santa. Thank you for coming to my lab, especially at this time of the year. I know you're very, very busy. Did you get my list, Santa?
Oh, yes.
You did get my list?
A long list.
Yes, well, I wanted some things, and I hope, did I get anything on my list?
Have you been a good boy?
I've been a good boy. Haven't I been a good boy?
Yes, I got some stuff here. Well, oh yes. Here's something you asked for.
Oh, yes, I asked for a science book.
It's a hot item.
Can I open it and read something in it here?
Sure.
You were right, Santa. This is a real hot book. Thank you, Santa. This was on the top of my list.
You're welcome. Well, here's another thing.
Yes, I wanted some balloons. I just love to do experiments with balloons, and I'm going to do some more experiments with balloons, and that's a good supply that I will use right away. Oh, yes. This is, it's not real money. It's just a piece of paper in the shape of a $10 bill. And I'd like to show you, Santa, and everyone else, what we can do with this. I take this and hold it over the flame like so, and it disappears into thin air, just like that. You like that?
Yes. I love that one.
This is, it's called flash paper, as you and your elves well know, because you prepared this for me. Yes, I had some other things on my, oh yes, I wanted this very, very much. This is a bubble solution, which we will use in many experiments that we will do later on. Anything else?
Well, let's see. You asked for this. 2 pieces of glass tubing with a piece of rubber tubing in between and a clamp. I don't know what it's for, but you asked for it. There it is.
Well, it's for some special experiments which we will do later on too, Santa. Thank you very much for everything that you have brought me. And as a special salute to you, Santa, I would like to ask Fred Juergens to come out, our lecture demonstrator, and give you this very special salute.
Oh, hi, Fred.
Okay, Santa, you've seen some of the experiments that Professor Shakhashiri is doing. I've got some beakers set up here, too. There are all kinds of things that you can do with beakers, and so you can stir them, and then you notice that there's some sound. And so I set up a whole bunch of beakers here to serenade you for your special holiday, okay? Well.
Thank you, Fred. Thank you.
Merry Christmas, Santa.
My favorite song.
Santa, I see that you have your Science is Fun button on, and so I'd like to do some experiments. Are you ready and prepared to do some experiments?
Oh, wait, just a minute. I got something else in my bag. Aha.
Oh, yes, sure. Eye protection. Very, very important that we have that. This experiment that I'm going to do is with some small crystals that I will put at the tabletop like so. And then I'm going to take this clear and colorless liquid out of this flask. I'm going to pour the liquid on top of the crystals.
Oh. It looks like an upside-down icicle.
It sure looks that way, doesn't it?
I've seen those at the North Pole, but they grow the other way.
This is actually, you like that? Huh?
Very good.
This is actually the crystallization of something called sodium acetate coming out of a supersaturated solution. And I can tell you, Santa, that if I put my hand close to this upside down icicle, as you called it, that I feel warmth. That's because this crystallization reaction releases energy in the form of heat. Now, you don't have much heat up in the North Pole, do you?
Oh no, it's very cold.
Well, I would like to give you this, which actually has the very same chemicals in it as we just used, the sodium acetate and the water. And if you just press on it a little bit right here, we'll see what happens.
Okay.
Just press. There's a little coin in there. Press on it.
Yes.
Yeah.
A little coin.
Yeah.
Pressing.
Press. Yes. Yes.
It's turning white.
It's crystallizing just like this one did, right?
It's getting hot. Oh, I could use one of these for a hand warmer.
Exactly.
Up at the North Pole.
And I would like you to keep that.
Oh,
Santa.
thank
and
you.
The instructions on it tell you how you can regenerate this for many times of its usage.
Thank you.
Thank you, Santa, for coming. I know that you're very busy and you have to make many other stops, but can you stay for the rest of this program? Do you want Santa to stay? I have a place saved for you right there, Santa.
Thank you.
And I wish you the happiest of holidays.
Thank you. Merry Christmas.
Enjoy the rest of the program.
Merry Christmas.
Well, Santa, we're going to do a few more experiments that I hope you will enjoy and like. Let me take the candles out of the way so we don't, because we don't need them anymore. And I'm going to do this experiment by taking two liquids. They're actually, what does this liquid look like? Syrup. It's not syrup. It looks like oil. It's not oil. It looks like, yeah, but it's not that. It's a kind of a syrupy looking liquid, right? But it's not for consumption. There's the other one too. Now, for a chemical reaction to take place, what we have to do is mix the chemicals together. And we can tell when a chemical reaction is taking place if there's a color change. You see a color change here? So we can tell that there is a chemical reaction taking place. Some chemical reactions are very fast, as we saw with the explosive mixtures we had in the balloons, and some other reactions take a bit longer before they happen. And we have to work very hard sometimes to make a chemical reaction go. You can tell that I'm working hard at this, right? My hand's getting tired from doing all this. And lots of interesting things happen if we are patient. That's what we should do when we do scientific experiments. Be observant and be patient. Well, what I'm going to do now, because I'm really getting tired, I'm just going to catch my breath, stop this, and see what might happen. We'll keep an eye on this, you and I together, and we'll see if there are any changes that might be taking place. As we do that, what we will look for now is another experiment. Whoops, something is happening here. Can you see it happen? What's happening? What's rising? Is the beaker rising? No. What's in the beaker is rising, right? So we have a chemical reaction taking place, and let's get back. We might be in trouble here. This thing is getting out of control. Now let's stay in there. Now stay in there, stay in there. Won't listen to me, right? Oh, well. This is actually a chemical which we call a polymer. It's called polyurethane foam. It has a lot of interesting properties. One of them is the one that we're looking at right now. Another interesting property is that it's a good insulator. It's used for insulation purposes in cold places like Madison and elsewhere around the country. So this is a polymer, and it's called polyurethane foam. Of course, you all know about this polymer. What's this one called? Styrofoam, right. It's actually made of something we call polystyrene, and I'm going to show you one property of this polystyrene. This is a cup, so what do we usually put in cups? A liquid, right? So I have a clear and colorless liquid. I'm going to put this in the cup like so, and fill, whoops, what happened here? The bottom fell out, right? This liquid is called acetone. Acetone is commonly found in nail polish remover. And what the acetone does is it takes the foam out of the styrofoam. It looks like the polystyrene is dissolving in there, but it's not. It's just collapsing. And I will show you, very interestingly, if we take some of the packing materials that's made of polystyrene, also the peanuts, packing peanuts, we can put those in there. And you can see that they too collapse. Again, we're taking the air out of the structure that the polystyrene molded polystyrene had. All right, well, you see, Santa and everyone else, if you study chemistry and you know what you're doing, not only can you make certain things appear, but you can make other things disappear. All right. I would like you to look now at this part of the demonstration table where I'm going to mix two liquids. The first liquid is clear and colorless. And the second liquid is clear but colored. And these two liquids mix with each other. Actually, they don't mix very well. They form what we call an interface. And I'm going to use these tweezers, reach in there, and pick up what formed at the interface. And put it on this roller, and then turn the crank up.
Beautiful. Yeah.
Now we got all day to do this, right? This is a form of nylon, which is another example of the substances we call polymers. And the nylon rope that's being formed in this case is very, very long, and it's formed again at the interface between the two liquids that were mixed together. Well, enough of this, right? All right, now let me look at another polymer, a very interesting polymer. It's a white powder. It happens to be a solid, and I have about 5 grams of this solid. I'm going to put it in this beaker, which is empty except for air. So I'll just put in about 5 grams. And this beaker has in it some water to which we added some food coloring just to enhance the visibility. So I'd like you to help me now see how many times I can mix the contents of this beaker with the contents of this beaker. I'm going to go back and forth as many times as I can, as fast as I can, and you help me count, see how many times I can do this, okay? Here we go. Got to get all the liquid out, make sure it's all out. What has happened here is that that powder, that polymeric substance, has absorbed many, many times its volume in liquid. And this has formed now a gel. This has a lot of practical applications, including one application in gardening. If you want to keep some moisture away from certain parts of the garden, you can sprinkle some of that and then remove it later on. It also has a much wider practical application and a fairly common household item. And many of you know where we can find the material that is being used here. And what common household item do we have? Yeah? Candle? It could be in a candle, yeah, but it's not in a candle, no. More diapers, yes, it's in diapers. Yes, diapers. I heard your voice, you said that, yeah. And so diapers have the same chemical in them and absorbs, of course, the moisture and other things that need to be absorbed, right? Now I want to show you an interesting property of this gel. If you take some table salt and you sprinkle about maybe 2 or 3 grams of salt on top, and then you mix the salt with the gel, what this does, because the salt has what we call ions in it, it has ionic properties, sodium ions and chloride ions. Those ions destroy the gel feature that we observed, and you can see now the gel is becoming more liquidy. And the more you mix, the more you destroy the gel. And of course, we now can go back and add the liquid this way. Now you want to count again? You want to go back to counting? Huh? Well, it didn't all come out, right? It didn't all come out because the salt has not gotten all the way to the bottom of the gel. Okay, we'll do it one more time, okay? Almost, right? All right, we did that. All right, very
good. You don't need helium to make a balloon float. You can make any ordinary balloon float. All you need is a hairdryer. Turn on the hairdryer and point it straight up. Hold the balloon over the hairdryer and let it go. Watch the balloon float. Pass your hand between the balloon and the hairdryer and watch what happens to the balloon. Stay tuned, there are more fun balloon experiments coming up.
Now I would like you to focus your attention on this part of the lecture table where we have in front of me a series of cylinders. How many cylinders do you see in front of me? They're glass cylinders. They're 10 cylinders, and they have what in them? They have colored liquids in them, right? And you can see they are arranged in a special order. They're arranged by pairs according to the color of the liquid that's inside. I'm going to use the gloves to protect my hands from the next chemical I'm going to handle. This chemical is called dry ice. This is solid carbon dioxide. Its temperature is minus 78 degrees Celsius. It's really very cold, and it should not be handled with the bare hands because it will cause frostbite. Solid carbon dioxide changes from being a solid to a gas directly without melting. We call that process sublimation. So sublimation is taking place right now, but we don't see it. That's because carbon dioxide gas itself is colorless. It's invisible. It also has no smell. We say it's odorless. But yet the sublimation is taking place as we speak. So I'm going to take now, you watch what I'm going to do. I'm going to take some chunks of this dry ice, and I'm going to put them in the cylinder in a very special way, and you tell me what this special way is as we go along, okay? Did I put the dry ice in every cylinder? No. I put the dry ice in every other cylinder, and you see the bubbles? Those are the carbon dioxide bubbles. They're coming from the what? Sublimation of the dry ice. And the carbon dioxide combines with the water to form carbonated water. It forms carbonic acid. And the colors that you see some interesting color changes? Do you like that? We see these color changes because we have dyes that change their color when we change the acidity or the basicity of the solution. These dyes are called acid-base indicator dyes. You notice the change was pretty rapid in this case, pretty rapid in this case, pretty rapid in this case too, right? In almost all cases. So that's one thing we have to be always paying attention to as we do these experiments. Now, in addition to the bubbles, you see something coming off the top here. What do you think this is called that's coming off the top? No, steam is invisible. You can't see steam. It can't be carbon dioxide either because carbon dioxide is invisible. What is it? Fog. That's what it is, fog. It's like clouds, right? It's condensed water vapor. The water vapor is condensing on the carbon dioxide that's coming out from the top of each cylinder that has the dry ice in it. And you notice that the fog is moving downward. That tells us, if we didn't know it, that carbon dioxide is denser or heavier than air. And if we did know it, it just reminds us of it. Isn't this a very pretty effect? Huh? Now for the next part of the experiment, I need some hot boiling water, and I don't see it here. Can someone please bring me some hot boiling water? Can I have some help in bringing that out, please, huh? Hi, Bucky, and welcome to my lab. Bucky, I see you have your goggles on, which is very, very good on your part. And so together we're going to do this experiment. This is the next part of this experiment. This is what's this? What is this called? It's a dishpan. It's empty except for air, right? I'm going to take the hot water that Bucky brought in and put it in. You see anything coming off the top? No, steam is invisible. You can't see steam. It's water vapor, condensed water vapor. Water vapor itself is also invisible. So I'm going to take some more dry ice and dump the dry ice in this hot boiling water.
I'll need Rudolph tonight.
This is how they make fog in the movies sometimes. They take hot boiling water and add dry ice to it. You like this, Bucky? Bucky likes this. Do you like this too? Right. Bucky, I'm so glad you're able to come to my very special Christmas lecture. This is the 28th year that Bucky makes an appearance in my special program. And Bucky, I know you're getting ready for final exams. Are you studying, Bucky? Are you gonna graduate in time, Bucky? You're gonna make it in 4 years? 4 years. Bucky's gonna graduate in 4 years.
Good job, Bucky.
Bucky is pretty smart. And I know, Bucky, you have to go study for final exams, but would you like to stay for the rest of this program? Would you like Bucky to stay? All right. I have a special place for you right next to Santa. I'm going to do some experiments at this end of the table. I'm going to use a very cold substance, even colder than dry ice. This is called liquid nitrogen. Liquid nitrogen is a liquid at a temperature of minus 196 degrees Celsius. Very, very cold, and it's kept in what we call a Dewar flask. It's really a thermos bottle, that's what it is. And it's a liquid, and it boils at minus 196 degrees. You can see it's a colorless liquid. You see some stuff that comes out of the mouth of this Dewar flask? Yeah, what is it called? Condensed water vapor, right? That's what it is, condensed water vapor. So we're going to take a smaller Dewar flask and fill it up. And then I have a cylinder. I have a gas cylinder filled with oxygen gas. This cylinder that contains the oxygen is going to be the source of gaseous oxygen that I will allow to flow through this copper coil, which I will put inside a thermos bottle, a bigger one. That will be filled up with the with the liquid nitrogen. And then what I'm going to do is turn the valve on and allow the gas to pass through. Can you hear the gas coming through? And if you watch closely, you begin to see something interesting happen. I just let go of this piece of tubing, and it's held up in the air like that, right? That's because the cold liquid coming through, which I will collect in this tube, is liquid oxygen. And we're going to examine the properties of liquid oxygen and liquid nitrogen in just a moment. This is a very cold liquid. It is a liquid that boils at a temperature different than liquid nitrogen. If liquid nitrogen boils at minus 196 degrees Celsius and liquid oxygen is able to be condensed in liquid nitrogen, then the boiling point of liquid oxygen must be either higher or lower. Don't let the minus sign confuse you. Think about that in terms of the condensation of the liquid. So let me just now stop this, take this out, and set it down carefully. And I'll lift this up, and you see what color is liquid oxygen? Yes, it's pretty blue, not just blue, right? Well, it is really blue. And I'm going to do an experiment with this magnet that I have. I'm going to show you how powerful this magnet is. I'm going to take my pocket knife, put my pocket knife in there. Whoops, see, it's really held in there tightly. I can even lift it up with that. That's how powerful this magnet is. And what I'm going to do is take the liquid nitrogen and let it pass through the poles of the magnet. You see what happens is nothing. The liquid nitrogen passes through. That's because the nitrogen has no magnetic properties similar to the pocket knife that I use. But if I take the oxygen, I hold this very carefully. Let me put the gloves on because it is safer that way, right? I don't want to get frostbite. And put the liquid oxygen through the poles of the magnet. You see that the liquid oxygen stays in there until it evaporates. That tells us that liquid oxygen has magnetic properties. We call that paramagnetic liquid. So let's do it again and see what happens. It sticks in there until the liquid evaporates. This is probably the first time for many of you that you've ever seen a liquid held between the poles of a magnet, right? Here we go, the last time, okay? Now the liquid oxygen in this form is very concentrated. That's why we need to keep sparks and flames away from it. And I'd like to show you one other interesting property of liquid oxygen. I've got this beaker and I have a cigarette here. Let me just light the cigarette. People like this stuff. So I'm going to put that cigarette in there, and then I'm going to take my liquid oxygen, and you're watching this, right? Here we go. That's what I think you should do with all cigarettes. All right, so let's do some more experiments with balloons. We have this balloon that's up here. I want to bring this balloon over to the other side, and I'm going to take some liquid nitrogen, if I have some left here. I have some left here. Doing experiments with balloons is a lot of fun. Do you remember what was in the other green balloon before? Yes, helium. So what I'm going to do is take the liquid nitrogen and put it on top of the balloon. Some of you are covering your ears. I can see that. It's because you learned from experience what might happen, right? So what's happening in this balloon as the liquid nitrogen cools off the helium atoms, the balloon is collapsing, right? It's shrinking. So I take the liquid nitrogen away, and the balloon goes all the way up to the ceiling. Well, I'd like to do some more experiments with balloons, and so I'd like my special assistant Elizabeth to come up now. Are you ready to come and help? All right.
Yeah.
Come around. Hello, Elizabeth.
Hi.
And of course, we have the goggles for you. We're going to do some interesting experiments. We're going to actually do an experiment with balloons and an experiment with some dry ice. So I want to get some more dry ice, which I have over here. And I'm going to crush this dry ice to make it into a powder. And then I'm going to put the powder inside this balloon. So can you hold this up for just a...
Sure.
And I want to get some dry ice. I need my gloves, right? Safety always is paramount, right? So I need my gloves to handle the dry ice. I put about 4 chunks of dry ice in there, and then we both have our goggles on, right?
Yeah.
So just powder this. Now what's happening to the dry ice as we're crushing it, and the dry ice that's sitting in the bucket over there?
It's sublimating.
Yes, exactly. It's changing from being a solid to a gas directly through the process we call sublimation. So I'm going to take this, make it into a powder, and then I would like you to help me. Let me hold this now.
Okay.
Can you take this scopula right there and fill this balloon with dry ice,
Sure.
powdered dry ice. One more scoop.
Okay.
All right, the next thing I'm going to do is take the balloon off of this funnel, and I'm going to tie it. And what's happening to the dry ice all along? It's subliming, right? And when it sublimes, what's it doing to the balloon?
Inflating it.
It's inflating the balloon. The gas pressure inside is sufficient to inflate the balloon. So we'll set this over here and watch it and see what else might happen to it. We have a whole bunch of balloons that were brought over by you-know-who, right? And can you help me inflate this balloon?
Sure.
Okay.
How's that?
All right, that's great. That's great. I'm going to tie this balloon real quickly for you, and then I'm going to give you this very long and sharp needle.
Okay.
It's safe to handle. I'm just going to ask you, can you put the needle through the balloon without having the balloon pop?
I don't know.
Would you like to try it?
Sure.
All right, here we go.
Okay. Whoa.
That didn't work very well, did it?
Nope.
Well, perhaps there's a way to do this, okay? Would you like me to try?
Sure.
All right. First, we inflate the balloon. We let some air out, right? And then what's the next thing we do?
Tie it.
We tie it, all right? And then we take the needle. And I'm going to take this needle, and I'm going to dip it in some Vaseline, just to lubricate it a little bit, all right?
Okay.
So then I'm going to take this needle and stick it, where are you going? Come back here. Come back here.
That's okay.
You have confidence in what I'm doing, right? Huh?
Of course.
Huh? Well, come on back here then. Come on back here. Right? So take, you want me to do it first? Okay, here we go. See? Now you can get closer, right?
Yeah.
See, it didn't pop, right?
Wow.
And we see the thread coming through the two holes in the balloon. You see that? Huh? So what's happening to the balloon?
It's deflating.
It's deflating. It's shrinking. Of course it is. It's got two holes in it, right? Can you feel the air coming out?
Yep.
Huh? Do you think this is a special balloon of some sort, or just an ordinary balloon that Santa and his elves prepared for us?
Guess it's just ordinary.
I think it's ordinary. So you take the needle and put it through. And now, you're right. You knew that was going to happen, didn't you? All right.
Well, is there any way I can do this at home?
Can you do this at home? I suppose you can. Let me suggest to you some ways in which you can do this. All right,
Okay.
Here you go. First you have to do is inflate the balloon. All right, what's the next thing we do?
Tie it.
Tie the balloon, right. And the way you do this at home, because you don't have a long needle like this, most people don't, right? Do you have this needle at home? No, you don't. But you do have at home are small pins, right? You have small pins at home, and you also have some Scotch tape at home. So could you take a piece of Scotch tape, please,
Sure.
and put it at the end of the balloon opposite where we inflated, right there, yeah? And then would you reach over for one pin? And now you can stick that pin through the Scotch tape. Here's one stab, 2 stabs, 3 stabs, 4 stabs, as many stabs as you want. And the balloon is not popping, right? Ah, there are holes, yes. I can feel the air coming out. Very good. Now, what else can you do to this balloon? You can put the pin someplace else. What will happen?
It'll pop.
You don't want to do that, do you?
Not particularly.
All right. We'll leave this balloon over here. Well, that was very good, Elizabeth. Thank you very much for all the help that you have given me. Happy holidays to you.
Happy holidays to you too. Do you want to try some fun experiments at home? Check out the Science is Fun website at this address. You'll discover fascinating facts about chemicals and other great science information.
All right, now we'll do some more experiments with balloons. Remember, Santa brought this, what did he call it? Whatever, two pieces of glass tubing and a rubber tubing and a pinch clamp and so on. Well, we're going to do some more experiments with balloons. We're going to do an experiment by taking this yellow balloon, attaching it to the end of the glass tubing, and then I'm going to inflate it. So nothing happened. How come nothing happened? Because the pinch is right. The clamp is pinching there, right? So, okay. So we inflate this, and we get another balloon that Santa brought, and we put this balloon, we inflate this balloon like so. We put this balloon at the other end, and now we have balloons, different colors and different size, right? Now the question is, whoops, this one is slipping off, this one is slipping off. I'm going to, there. All right, now the question is, what would you predict will happen if I release the clamp that's pinching the rubber hose in here, huh? Well, some of you, I want you to think about this, right? Some of you are thinking maybe the big balloon will get smaller and the small balloon will get bigger. Some of you might be thinking that both will become the same size, right? How do we get to find out? We just do it. We do the experiment, right? We cut out all this talking and do it. So how do I do it? Just let go. And what happened? The small balloon got smaller and the big balloon got bigger. Is that what you predicted? Well, some of you are saying yes, but most of you are shaking your heads and saying no. Now, I think everyone here who has ever inflated a balloon knows the explanation as to why the small balloon got smaller and the big balloon got bigger. It's not like, other things that happen in society. The rich get richer and the poor get poorer. No, it's not like that, no. There's an explanation for it. When you inflate the balloon, when did you have to work the hardest? At the beginning or at the end? The end. At the beginning. At the beginning is when you have to. And so when the balloon is stretched out already, then it is easier to pump it up some more than it is to pump up a balloon that has not been stretched as much. By the way, we still have this balloon over here. Remember what was inside this balloon? Dry ice, right? So let's see if we have some more liquid nitrogen, and we can put the liquid nitrogen on top of this balloon and see what happens to it, all right? Here we go. We add the liquid nitrogen to it. And this balloon has collapsed. I'm out of liquid nitrogen here, but you can see that it is actually, I have more liquid nitrogen. Not. There we go. And what's the white stuff inside the balloon? Dry ice, right? Its sublimation temperature is minus 78 degrees. That's higher than the boiling point of liquid nitrogen. So it's right there. When it warms up, you know what's going to happen when it warms up. All right, here's one more experiment we're going to do with, well, let's see. We're going to do it with, what's this? It's a coffee mug, right? And do you suppose I can hold this mug up in the air without touching it? Oh, some of you are saying yeah. Some of you are saying no. All right. I'm going to show you how you can use a balloon and an empty coffee mug. It's empty except for air. And let's watch and see what happens. Right there. Now, what do you suppose will happen if I let the air out? It'll fall, right? So I better catch it first. I'll let the air out, right? And you all know how to do this, right? You can try it at home. What's important is that you try to think as to why it works, right? Not just to show somebody a neat trick, but think about the reason for it. So we do it again. And you can see it's just bouncing here, right? And you can also see that if I don't release the air and I try to pull it out, I have to work to pull it out, and there it came out, all right? So that's kind of a hint as to what might be going on. What will happen to this balloon if I let go of it? Let's find out, right? So it just goes all over the place. All right. So this experiment we're going to do in a fish tank, exactly. And this fish tank is empty except for air. What we're doing is adding some dry ice. Into the fish tank, and the dry ice, of course, sublimes. It changes from being a solid to a gas directly. Now, Santa Claus brought me something else that I had asked for, which is bubbles. I love bubbles. I like to play with bubbles, don't you? Well, what do you normally do? You take some, you take the wand out, right, and you blow. Oh, we can do better than that. Just one bubble? No bubble this time. 3 bubbles this time. Oh, let's do better. There we go. Now what I'm going to do, you see, is blow the bubbles on top of the dry ice. And what's happening to those soap bubbles is that they are what? They're floating. What are they floating on? Carbon dioxide. They're not floating on air. In air, you know what happens in air? They go way down, right? But they're floating on the carbon dioxide gas. Where did the carbon dioxide gas come from? From the sublimation of the dry ice. We'll do this experiment with the burner and using a large flask like this that has a colored liquid at the bottom. You can see that, right? This is actually an acid-base indicator, and this is the color of the indicator when the solution is not acidic. In this flask, we also have some oxygen gas, but we can't see the oxygen gas because it is colorless and invisible. So I'll take this either way like so, and I'm going to use a solid called sulfur. I'm going to take some sulfur, use this spoon. I'm going to burn the sulfur. And when you burn sulfur in the flame like this, or any other way, you get sulfur dioxide. And this burns in a very interesting way. Actually, you can see the flame of the sulfur burning if we turn the lights down. So turn the lights down, please. And you'll be able to see a characteristic flame of the sulfur right there. And if I take this and stick it inside the flask, you'll see what happens. That's because there's oxygen in there. You like that? And if we turn the lights back up, very pretty glow, isn't it? You can see that there are fumes there of sulfur dioxide. Now, sulfur dioxide combines with water to form acid rain. And if the solution becomes acidic, what color is the liquid at the bottom now? Blue. And as the sulfur dioxide dissolves in, you see any change in the color? Green, yes. And what else now? So this is how we find out about acid rain, because sulfur dioxide causes acid rain to happen. At this time, I'd like to invite Fred Jorgens to come out and do a special experiment.
Thank you. I've got a long tube here that's got a mixture of gases in it. They're invisible to the naked eye, but I know they're in there because I put them in there. Okay? And you've learned from Professor Shakhashiri that sometimes when you put a match to or a torch to balloons that have gases in them, something happens, right? So we're going to do the same thing with this tube. I'm going to light a match. I'm going to stand up here on this stool. Santa, thanks for warning me to be careful. You know, I don't have my glasses on. I really need a pair of safety glasses before I do this. Thank you. Okay, so we're going to do this in the dark. I'm going to light the match. And you can all see the match up here. I'm going to take the stopper off and drop the match in.
We can see some things inside that tube, Fred. What's that?
Well, there's a yellow solid inside the tube now. It's sulfur. You know, Professor Shakhashiri burned some sulfur and made sulfur dioxide. We were able to make sulfur in this reaction, and it's on the inside of the tube now.
Fred, I would like you and everyone else to take a look in slow motion at this very same experiment that we just saw. You won't hear any sound again. There's Fred. Oh, he's getting out of the way quickly. Fred. I'd like everyone to know that Fred Jorgens has been the lecture demonstrator at the university for 20 years, and he's retiring in about a week or so. And I have, yes.
Thank you. Thank you.
And this very special Christmas lecture is dedicated to you, Fred, in recognition of your excellent contributions to our university, to our community, and to the profession. Congratulations and best wishes to you.
Thank you very much. I got one more thing. Thank you. You know, before I leave, I'd like to do one more demonstration for you. Professor Shakhashiri has been showing you lots of things that are science, because in principle everybody can understand how to do these things, you know. There are other kinds of things that you go to programs to see that are called magic. That's where only a few people know, and the magician just doesn't tell you how he cuts that lady in half, or how he doesn't, you know. And if nobody understands it, we really call those kinds of things miracles. Well, I'd like to show you one more demonstration, if you can sort of focus on this beaker right here in front of me. I've got two clear and colorless liquids that I will pour into this other clear colorless liquid, and we get this gorgeous yellow color. Now, in one sense, that's science, because we know how to do that. But isn't it a wonder that we can mix colorless things and see something yellow come out? The wonders of science are just what has kept me doing this job for 20 years. You know, it's been a wonderful experience being at the university. I've enjoyed it tremendously, but it's just time for me to do something else now. You know, so I'm going to have a good time doing that, and thank you very much. Okay.
I'd like to ask you now to focus your attention on this special glass spiral assembly. And I'm going to take a clear but colored liquid and mix it with a clear and colorless liquid. I'm going to do this in the dark. So if we can have the lights off, we'll see what happens as I mix those in the dark. This is an example of what we call a chemiluminescent reaction. This reaction releases energy in the form of light, not in the form of heat. Chemiluminescence is the name of this phenomenon that we have just observed. All right, so we go now to this part of the lecture table where I have a large beaker. In fact, I want you to look at this beaker. The volume of this beaker is 4 liters. If you look at this beaker, you just learned how big 4 liters is. You can't unlearn it. You may forget it, but you can't unlearn it. I put a Teflon-coated magnet in it, and I'm going to then turn the motor on so we can mix chemicals as I add them. The first liquid is clear and colorless. At least in the flask it is. When I add it down there, it's not so clear. And the second liquid is added. Anything exciting happened so far? Not really, just the volume change, right? And I add the third liquid. Is there anything happening? How come I don't see anything happening? Because I'm not looking. What's the big deal about looking? The last time I looked, the color of the liquid in the beaker was blue. So, if I look right now, right this minute, you tell me when to look, okay? Right now, right this second. You sure? Right now. See, it's blue. Every time I look at it, it's blue. You tell me when to look. Right now. Now. Right now. See? It's blue. Every time I look at it, it's blue. Right now. Right this second. You sure? Right now. Right now. Right? Right now. Blue. Oh, keep looking, she said. Keep look. Oh, wow. That's... I should be looking all the time, like you are looking all the time, because if I don't, I miss out on important and interesting things that you did not miss out on. Well, this brings to an end our very special Christmas celebration with you this holiday season. I wish you the best and the happiest holiday season. And remember, no matter what you do, that science is fun. Thank you very much. Happy holidays.
To order a VHS copy of this program, please send a check for $30 to 1997 UW Christmas Lecture, Department of Chemistry, University of Wisconsin, Madison, Wisconsin 53706. Please do not send cash. Credit card and COD orders cannot be accepted.